So our first topic beyond review is waves. In John Coley's book, vibrations and waves are together in the same chapter. So vibrations, also known as oscillations or periodic motion, is the last topic that we cover in Physics 8. So I think it doesn't hurt to do a little bit of review of vibrations and oscillations. So one point here is that anytime you have something in stable equilibrium, so you see if this marble tries to move away from its equilibrium point at the bottom, then if it tries to move this way, gravity will push it back where it came from. If it tries to move this way, gravity will push it back where it came from. So if we displace it just a little bit, it will slosh back and forth. So it's a sort of universal phenomenon that anytime you have an object which is at a stable equilibrium point, and of course, if you were in Physics 8, or if you take Physics 8 next year, the whole point of what we do when analyzing the parts of a structure is to make sure each piece of the structure is in stable equilibrium. So you can always displace an object with respect to its stable equilibrium point, and then it will undergo vibrations, oscillations, periodic motion, all names for the same thing, with respect to that point of stable equilibrium. So when we build things, you want them to stay put. We put them in stable equilibrium. Anytime something is in stable equilibrium, a small displacement with respect to that equilibrium position will result in vibrations back and forth. And this is why vibrations are such a ubiquitous phenomenon. So we're going to go on now and review our two favorite examples of vibrating systems. One of our two favorite oscillating systems is the mass hanging on the end of a spring. So usually the mass is also known as the bob. So if I attach, so here's a spring, we don't know the spring constant of this spring. So if I put the mass on the spring, it's going to oscillate back and forth like this. Now if I take the same spring and I use a smaller mass, it will oscillate more quickly. And then an even smaller mass will oscillate even more quickly yet. And the result that we found in Physics 8 was that for a mass on the end of a spring, the natural period of oscillation is 2 pi times the square root of the mass divided by the spring constant. So the spring constant is measured in newtons per meter. So newtons are a unit of force, which is a unit of weight also. So if we put a known weight at the end of this spring and we measure how many meters it extends from the relaxed length of the spring, we can divide those numbers and get the spring constant. So here's a 1 kilogram mass. So that is 9.8 newtons, about 10 newtons, multiplying by the acceleration due to gravity. So if you look where the bottom of this spring is now, and then you see what happens when I add the 1 kilogram mass, the spring became 15 centimeters longer. So each one of these stripes is 10 centimeters. So I measured out 15 centimeters longer. So that gives us a spring constant. I worked it out on the board where you can't see it. That gives us a spring constant about 65 newtons per meter. And now we can work out the natural period of oscillation. So that's 2 pi times the square root of the mass divided by the spring constant. So for a 1 kilogram mass here, the natural period of oscillation should be 0.78 seconds. So if we let this thing bounce up and down 10 times, that should happen in 7.8 seconds. So let's see how well we did. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's pretty good. Okay, we predicted 7.8, we got 8.0. Now if I do the same spring, so it's the same spring constant since it's the same spring, but I use a smaller mass. So this is a 500 gram, half a kilogram mass. So that's going to be, instead of 9.8 newtons of weight, that's going to be 4.9 newtons of weight. So then I worked out, so now the period will be 2 pi times the square root of mass divided by spring constant. That works out to 0.55 seconds. So if we let this thing bounce 10 times, that should be 5.5 seconds. You can also notice that the spring extends less far. It should extend half as far, only 7.5 centimeters instead of 15 centimeters with half the weight on the end. So now let's see what happens when we let this bounce 10 times. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5.5. We predicted 5.5, right? So the period we worked out, where you can't see it on the board, is 0.55 seconds. 10 times we expected 5.5 seconds, so this time we were right on the money. Now if I do a 200 gram weight, that's 0.2 kilograms. You should see this go down only, let's see, 6.5, about 1.3, 1.4 centimeters. Won't go down much at all. Let's see if that seems about right. Yeah, it seems about right. And then, so now it should oscillate even faster because that square root of the mass upstairs, which is giving us the period, is even smaller. It's 20% of what it was the first time, well then the square root of that, so it's about something like 40% of what it was the first time. So let's count. Okay, it might be a little too fast for us. Let's count how fast this thing bounces up and down. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the number I worked out on the board was 0.35 seconds for the period, so 10 times should be 3.5 seconds, 3.5 seconds, and we measured 3.7 seconds. Again, that's pretty decent. So if we make the mass smaller, then that makes the oscillation period shorter. It makes the frequency is the reciprocal of the period. Period is measured in seconds, frequency is measured in cycles per second. So if we make the mass smaller, it makes the oscillation frequency faster, it makes the period of oscillation shorter. Now let's try varying the spring constant. So the easiest way to see that these two spring constants are different is to attach the same mass to the two springs and see what happens. So here in each case is a 500 gram mass. So I'll attach it to our first spring and I'll attach it to our second spring. And this spring is much less stiff. So a less stiff spring has a smaller spring constant. And a smaller spring constant gives us a longer period of oscillation or a smaller frequency of oscillation. You can't even see this, it's a little off camera. Okay, here's the first spring we started out with. Here's a much less stiff spring. So that period of oscillation has the spring stiffness, the spring constant downstairs. So a less stiff spring means a longer period of oscillation. So let's see what happens when we start these two bobs on springs oscillating. So this one is much more slow than this one. So the period of oscillation is longer for the less stiff spring. Okay. Then we have another spring which is considerably stiffer than the original, and you can see that because, again, we'll take our two standard half-kilogram masses. I'll put this here. I'll put this here. Oh gee. This might be a problem because it extends so little that it's going to crack, it keeps bumping into itself. Let's see if we can make this work. I can double the mass. That's a little better. So that's a kilogram. That's a kilogram, so it's the same. There's 1 kilogram here, 1 kilogram here, and I can make these two bounce up and down, oscillate. And the period of oscillation is going to be shorter for the stiffer spring. Frequency will be larger, period will be smaller for the stiffer spring. Okay, I have to keep the amplitude low so that it doesn't collapse onto itself. That's pretty good. Another thing I can do is I can put 2 kilograms at once on this spring. And then I'll put those same 2 kilograms on this spring. Well, now it's crashing this way, but I guess I can move it over here. So the less stiff spring oscillates with a longer period, a smaller frequency, and I can go back now to the more stiff spring, and we're going to see a shorter period, a higher frequency. Good. And then another thing to notice is that the period of oscillation is for natural free oscillation. You just bump it and let it go. So the period of oscillation is independent of the amplitude. So I guess we can do that by, we'll go back to our original. This is 1 kilogram on the first spring, so we predicted 0.78 seconds period to 7.8 seconds for 10 oscillations. So I'll try to make this go gently. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So we predicted 7.8, we got 8.1. Now I'll try to make it go with a larger amplitude. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, again, 8.1. So we changed the amplitude quite a bit, and the period didn't change. So that's true as long as the system is linear in mathematical terms. So essentially that the spring constant doesn't change as you stretch the spring more or less. Sometimes in real life, if you stretch a spring a whole lot, the spring constant will change a little bit. But for relatively small oscillations, this is true. The period of oscillation is independent of the amplitude. Okay, we're going to do the same thing now. Our first of our two favorite oscillating systems, the mass on the spring. we're going to do it with a much bigger spring. It's a garage door spring. And we're going to do it with a much bigger, that's a much stiffer spring. We're going to do it with a much bigger mass. The mass is going to be me. So I weigh 70 kilograms, just over 150 pounds. And I have a helper here, the esteemed Bill Burner, our semi-retired demonstration guru. So we're both wearing our masks. And so here we go. I'm going to get up there, and now this spring, when we stretch it, it's kind of, see, notice that it's all crunched together now. So I can't measure the spring constant by going from its completely relaxed position to stretched out, because there's a nonlinear effect. So I'm going to get on the seat, and then we're going to do a delta. We're going to add a 20 kilogram mass and see what the change in length is, and then we'll subtract that 20 kilogram mass. And we can use that delta L corresponding to that change in force to measure the spring constant. So here we go. The last time I did this trick was pre-pandemic. I've probably undergone the pandemic loss of muscle mass. So we're going to see how far the chair is off the ground when it's just me on the chair. And the number is
1.69 meters.
1.69 meters. And now I'm going to grab a 20 kilogram weight, and we'll see how far down I go.
Okay, and we are at 1.4 meters.
1.40 meters off the ground now. This thing's getting heavy. Whoa.
Yes.
It's almost 50 pounds. Whoa, all right. Okay, so we will work out later what our inferred spring constant is. So we know my mass, I'm 70.0 kilograms. I just stepped on the bathroom scale a moment ago. And now we have enough to calculate the spring constant. So now let's figure out the period of oscillation. So we'll do our usual trick where we'll count how long it takes to go 10 cycles. So I need to bounce a little bit. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that was 19.3 seconds for 10 oscillations. Let's do it one more time, just to get another run here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 18.9. And well, we could try let's try a very small amplitude. I worry a little bit about the very large amplitude. Let's see, let's try a very small amplitude. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 19.7. And we wanted, okay, we can try a slightly larger amplitude. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it seems like we saw no amplitude effect. And now I'm going to get back on solid ground. All right. And let's do the numbers. I'll probably do the numbers again on a light board at home, but let's do the numbers. So, we said mass is 70 kilograms. Oh, what's the spring constant? So, spring constant is delta M times G over delta L. Do you remember those numbers?
1.69. 1.69 and 1.4.
Okay. So 20 times 9.8 divided by 676. Times 9.8 divided by, okay, and then we're going to say that the period is 2 pi root m over k. Two times pi times the square root of 70 divided by 676. 2.02. So we expected a period of 2.02 seconds, and we got a period of 1.97 seconds. I would call that pretty decent. And yeah, I think our numbers were in the range of 19 to 20 for 10 oscillations. So yeah, hey, pretty good. That's the best we've ever done with this experiment. Previously, I tried doing it, measuring the change in length from all the way collapsed up to when I sit on it. And I think the trouble is that it's not a linear response of the spring over that huge range. But if we just do my mass and then my mass plus 20 kilograms, that seems to work out okay. Sorry about the muffled voice, but we're working together in the room, so we're staying safe this way. The next of our favorite oscillating systems is the pendulum. So that's a bob on the end of a string. And we treat the bob as if it's a concentrated mass all at one point. So that means the physical size of the bob is much smaller than the length of the string. And then there's some pivot point up here. And just barely visible on the board is that we worked out that we saw this in physics 8, so this is basically review. The period of a pendulum is 2 pi times the square root of the length of the pendulum divided by the gravitational acceleration near Earth. That's the familiar 9.8 meters per second squared. So if you put in a length of 1.0 meters you get a period of 2.0 seconds. If you put in a length of a quarter meter, 0.25 meters, you get a period of 1.0 seconds. And then in between, you can put in a length of a half meter, 0.5 meter, and you get a period of 1.4 seconds. So I adjusted the string length here to be 25 centimeters, a quarter of a meter, which is sort of plausible here from the 10 centimeter spaces. So here's 10, 20, 25. Let me get this out of the way. So now we expect the period of oscillation for this bob on the end of the string to be 1 second. So then if we let it go back and forth 10 times, we expect that to be 10 seconds. So let's see how we do. By the way, this cool digital timer, this was actually built by a UPenn class of 2020 student. He's now working for Facebook, but he worked with me from his years in high school. So he built this using an Arduino microprocessor back when he was a junior in high school, maybe a senior. Anyway, I digress. I often digress a little. So let's, and you can neat remote control too. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, hey, pretty decent. All right, we predicted 10 seconds, we got 10.1 seconds. Now let's try it with a slightly larger amplitude. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, pretty good. 10.4, we predicted 10. And then we can try it with a smaller amplitude. So the pendulum was one of the early examples of a clock you could use to tick out, to measure things that are on the same order of magnitude as a human heartbeat, say. If you wanted to, measure number of beats per minute, a pendulum is a pretty good low-tech stopwatch, because all you need to know is the length of the string. So, okay, small amplitude. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, again, pretty decent. We predicted 10 seconds, we got 9.8 seconds for the time it took to go back and forth 10 times. Now, let's try changing the length. So, I think I'm going to try to go all the way to 1 meter. Right, because 1 meter is way down here. Okay, let's go to a half meter. So, okay, of course this is a meter stick. I can't go all the way to 1 meter without first adjusting the camera. So let's first go to half a meter. So from the pivot point up here down to the bob should be 5 stripes. That seems quite plausible. 1, 2, 3, 4, 5 stripes worth. There's 50 centimeters. Okay. So now if we time this 10 oscillations, so we had a 1 second period at a quarter, at 0.25 meters. So at 0.5 meters, we expect a 1.4 second period. That's basically the square root of 2. So let's time it again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whoops, it didn't stop. Okay, here. So I think it was at the right place when we should have stopped it, but we didn't quite stop it. Let's do it again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cool. Okay, so we predicted 10 times 1.4 seconds, 14 seconds for 10 oscillations. We got 14.3. Good. Okay, now I'm going to adjust this to 1 meter. So you can see now that we've adjusted this to a length of 1 meter. Let's see how well we did. Here's the top. That's pretty good. So there's 1 meter of length. So 2 pi square root of length divided by the gravity constant near Earth should give us 2.0 seconds. And now, if we use the timer and let it swing back and forth 10 times, let's see what we get. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hey, pretty good. We predicted 2.0 times 10 is 20. We got 19.9. Science works. We could try it at smaller amplitude if we wanted. So here's a pretty teeny amplitude. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hey, again, pretty decent. All right. The pendulum. You can see why Galileo loved the pendulum as a way of measuring short intervals of time. Okay, the other of our 2 favorite oscillating systems is the pendulum. So we tried some smaller pendula earlier that were between 1/4 of a meter and 1 meter long. Let's try a pendulum in this case that should be a little over, should be maybe 2.5 meters long. Let's see, from the pivot up there to the center of mass of the bowling ball is going to be that is 2.92 meters, maybe 2.93. Okay. 2.93 meters, maybe I'll write that down somewhere. And I hate to spoil a surprise, but while we're here, let's also see how long it is if I sit on it. Well, let's try this a different way. The ball right now is about 42 centimeters off the ground, 35 centimeters off the ground. Okay, it adds about 0.07 meters. Okay. Okay, we measured the height, well, from the pivot down to the center of mass of the bowling ball, and it's about a I think it's a 14-pound bowling ball. So that's, I don't know, let's say something like 6 kilograms. So let's figure out what we expect the period to be with a length of 2.93 meters. I think it's going to be, well, I don't want to do math in my head. Let's see. So we'll say 2 times pi times square root of 2.93 divided by our 9.8 meters per second g is 3.44 seconds. Now let's count 10 oscillations back and forth of the bowling ball. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, 34.5. Hey, that's decent. We were expecting 34.4. That's a little too good to be true. Okay, so that was pretty decent. Let's try the same thing at a higher amplitude. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 34.5. So again, pretty darn close to our expected 3.44 times 10. Now, if you look at that expression for the period of a pendulum, which is 2 pi times the square root of the length of the pendulum divided by the gravitational constant, little g, there's no mass in there. And that's because the mass is the inertia in the problem, but the same mass also through the gravitational attraction between the bob and Earth provides the restoring force. So the mass cancels out. So it shouldn't matter if I replace this, let's say 14-pound bowling ball with a 150-pound person. So it's like a 6.5 kilogram bowling ball. Let's say we replace it with, or maybe we add to it, supplement it with a 70 kilogram person. So let's try that. Now the one little detail is that this is a piece of rope. It's not really an extremely tense string. It's just kind of a rope. And I just measured a moment ago that it stretches by maybe about 5 or 7 centimeters when I sit on it. That's not a big deal. Actually, it'll bring that 2.93 meters up to 3.00 meters. So we could call it the same thing, or we could do it exactly. So okay, so here I am as the bob. So instead of 14 pounds, we have 14 plus 150, 164 pounds. Or in kilograms, instead of about 6.5 kilograms, we have about 76.5 kilograms. So here we go. Okay, here we go. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so divide that by 10, you get 3.47. We predicted 3.44. It seems not to matter if the mass is about 6.5 kilograms or is about 76.5 kilograms. Nice. Let's just try the same thing at a much smaller amplitude. Zero, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nice, okay, so that's 3.49 per swing, dividing by 10. Again, that's pretty darn close to our prediction of 3.44. Good. Okay, so this is a contraption we call the transverse wave machine. So let me back up for a minute. And if you have a long chain of things that behave like oscillators when their next door neighbors are held fixed. So let's see what happens there. So if I take one of these, if I hold this thing fixed, and I hold this thing fixed, and I let this one oscillate, you see it oscillates, you can just barely see it, but it oscillates back and forth. So this thing, these are like a whole bunch of coupled to each other, coupled to their next door neighbors oscillators. So this thing is like a little mass, and there's a little spring between it and its neighbors. So it'll oscillate up and down. So it behaves like an oscillator when its neighbors are held fixed. And then if I move one of these things, its neighbor will move proportionally to how much it moves. So you want it to interact. You want it to be like an oscillator by itself, and you want it to interact with its nearest neighbors so that if I move, then my neighbor is motivated to move. So if you have such a thing, it also has to behave linearly, but then that's a medium in which waves can propagate. And waves, you know, they kind of have nice aesthetics. So the way this thing looks in detail, if you look down on it, is there's like a long piece of kind of thick piano wire going down the axis like a spine, and then perpendicular to that are a bunch of metal rods, and then on each one of those metal rods is like a little dumbbell with an equal weight on each side. And the piano wire is trying to return each one of these to kind of the horizontal position. And if two neighbors are misaligned a little bit, then a restoring force tries to realign them. So we also have a little glow-in-the-dark sticker on the end of each one of these dumbbells. And we have an ultraviolet light, sometimes known as a black light. So I'm going to turn down the room lights so that you can see, you can really focus on the motion of these dots. So the first thing to notice is that this medium, we've kind of created the medium with this set of coupled oscillators. It has a characteristic physical property called a speed of wave propagation. So if I make a pulse here, you'll see that pulse propagate down and come back. And I can make a somewhat different looking pulse, but it'll still propagate at that same speed. So this speed at which the disturbance propagates down the chain is a property of the medium. And in the simple case that we study most often, that property is just a constant. There are some more complicated media called dispersive media where that speed of wave propagation is a function of the frequency, but that's a more complicated case, so we're going to deal with the case where the speed of propagation is a constant. And we're also going to see, I think we'll see this on the light board, we're going to see that for the case of a taut wire, like a piano string, like you're just like playing a guitar string or a piano string, then the speed of wave propagation is the square root of the tension upstairs divided by the mass per unit length downstairs. That's not so easy to see just waving my hands, but we'll see it on the light board later. So now waves can be either transverse or longitudinal depending on whether the direction in which the disturbance propagates is the same direction or perpendicular direction to the direction in which each little particle of the medium is moving. So in this case, if I create a disturbance, the disturbance moves horizontally, but each little piece of the medium is moving vertically. So these are transverse waves. So we can make a pulse propagate as a wave down the medium. And then you can see interesting things happen at the end. We'll get to that in a moment. Or we can make periodic waves. So if we make a periodic wave, we can make one end go back and forth at a fixed frequency. And then eventually, after the kind of initial transients die out, you get a nice, this looks like a standing wave. It's kind of the same pattern again and again. And now notice if I shake it more slowly, lower frequency, we're going to see a longer wavelength. It takes a while for the transients to die out and for it to reach a new steady state. But if I shake it more slowly, you're going to see a longer wavelength. And if I shake it more quickly, you're going to see a shorter wavelength. Again, we have to wait for the transients to die out a little bit. So I shake it higher frequency, each piece is going up and down more times per second. We see a shorter wavelength. Lower frequency, so each piece is going up and down more slowly. We're going to see a longer wavelength. We might be able to get it to go even a little bit more slowly. It's tricky. You can try for a really low frequency. That's decent. I don't know. We can go a little faster than that. It's also not always easy for me to keep my hand moving up and down at an exactly constant frequency. Well, that's pretty good. Okay, so the relationship there is that the wavelength equals the speed of wave propagation divided by the frequency. We'll write that down. Or the easier way to remember usually is that the speed of wave propagation equals the product of the frequency times the wavelength. So, you could say, suppose I'm wiggling one end of a taut string to create sinusoidal waves. If I double the frequency at which I wiggle the end, how does the wavelength change? We'll probably do this on the light board instead of doing it right here, but you can see it illustrated here. So suppose I'm wiggling one end at a given frequency. Now if I double the frequency at which I'm wiggling this end up and down, what's going to happen to the wavelength? So the product, remember the product of that frequency and the wavelength is a constant called the speed of wave propagation. So if I double the frequency, I think the wavelength will be cut in half. Let's see what happens. Yeah, I think that's pretty good. So the ideal thing that a wave wants to do is to propagate forever down an infinitely long string or an infinitely long wave machine. So like if you shout into an open field, there's no echo. So it kind of wants to do this and just keep going forever. But sometimes the wave runs into an obstacle. So there are basically the three easiest cases to analyze are if the far end of the string is totally clamped or immobilized, and my colleague Bill is going to immobilize the far end. Okay, so there are basically three cases that we can study easily. One is that the far end is totally free. The other is that the far end is totally immobilized. And then the third is that there is a perfect energy absorber on the end so that the wave thinks that it's traveling down an infinitely long medium. That third case is kind of hard to arrange, but we can get pretty close. So right now the far end is completely fixed, it's immobilized. So then when the wave reaches the far end, it's going to come back with the opposite sign. And the reason why that makes sense, that it comes back with the opposite sign, is that for that point to be immobilized, it's as if the original wave and then the new wave that comes back, at the instant when they're both present at the end, they add up to 0. So it's as if you have the wave coming in plus the wave that goes back, and they cancel each other out perfectly. So that makes sense that they have opposite signs. So it goes up and it comes back with the opposite sign. We'll try that again. It goes up and then it's going to come back with the opposite sign. Yeah, that's pretty cool. It goes up and it's going to come back with the opposite sign. Okay, so if we keep an eye on the leading, if the part that's kind of coming first. So the part that's first is up. Now the part that's first is down. Yeah. Okay.
Yeah, exactly.
So the part that's first is up. Now the part that's first is down. That's good.
Larry Gladney always used to say,
the part that's first is up. Now the part that's first is down. Okay, so now if we make the far end be completely free, so it can just wave without any, so if we disconnect the mass from the far end, so then the far end can just wave in the breeze. This is kind of like shaking a rope and the far end of the rope isn't attached to anything. Then you'll see the pulse come back with the same sign. And actually at the instant when it's reflected, it'll be double the original amplitude. So you see it come back with the same sign. So if the beginning is up, then the beginning will be up again. So the front part is up, the front part is still up. So if the part that arrives first is up, then the part that arrives first is still up. See here now, the whole wave machine is shaking up and down a little bit. But again, here, the first part is up. The first part is up. Good. At the far end here, we studied two cases already. One was that the far end is completely clamped, it's immobilized. It's not going to move. So then when the pulse reflects, the reflected pulse has to have the opposite sign so that the two pulses add up to 0 here. The other case was this thing is just free to go up and down. And in that case, the reflected pulse has the same sign as the original pulse. And it turns out, if you like math, that the constraint turns out to be that the slope of the wave is 0 at the far end. But you don't have to remember that. And now the third case that's interesting is if we put what's called a dash pot at the end. And this absorbs all of the energy that comes in so that the wave thinks that it's propagating down an infinitely long string or wave machine and no reflection comes back. And I think we usually clip that right around here. So it's a little tricky to get just the right motion for this. Yeah, that's pretty good. So there's a tiny little reflection because it's hard to make a perfect energy absorber, but that's pretty decent. So let's do it again. Yeah, that's pretty. You even hear the little. You might be able to hear the little swishing sound from the water. It's basically a little pot filled with water. So there's the wave. You just hear a little splash, and the wave basically dies out with a very minimal reflection. All right, good. So one weird property of waves is that two waves can pass right through one another. So if you had two particles going in opposite directions and they went through the same point in space, then they would probably, I mean, unless they missed, but they would basically bounce off of one another. And, you know, they would both change direction. Well, depending on exactly the details of their masses and momentum, they would both be affected by this interaction. But if you have two waves traveling in opposite directions down the same wave medium, then actually they can pass right through each other undisturbed, except that during the time interval when they overlap, then their amplitudes add. So let's see, so Bill and I are going to send positive pulses toward each other at the same time, and it's really interesting when they meet. So, okay, on the count of three, we're going to send a positive pulse. 1, 2, 3. That's pretty cool. As you can see at the instant when they meet, of course, you know, there's a reflection after they bounce off of the far ends, but at the instant when they meet, notice that the amplitudes add, and you get something in the middle, which is about twice as high as the original. Let's try it again. So 1, 2, 3. Yeah, that's really neat. So you can see what appears in the middle is like the sum of the two original waves. We'll try that again, same way. 1, 2, 3. Cool. Okay. Now, what happens if I send a positive pulse and Bill sends a negative pulse? So we'll see that they should add to 0 at that instant when they overlap. Now, it's not going to be exactly 0 because we might not make exactly the same size pulse, but I'll make an up pulse, Bill will make a down pulse. 1, 2, 3. Cool, yeah. So we'll try it again. Maybe we'll try a slightly longer wavelength so it's a little more obvious. What makes it more obvious? I don't know, we'll just try it.
I think short because it's more abrupt.
Okay, let's make a short pulse. We'll make okay, I'll go up, you go down. A short pulse. 1, 2, 3. Okay, that's kind of cool. And then let's try a wider pulse. So let's see. So 1, 2, 3. I guess, yeah, I don't know. 6 on one, half a dozen on the other. So I'll go up, you go down. 1, 2, 3. Yeah. So the two pulses basically pass through each other, each one basically undisturbed except during the moment when they overlap. And at the moment when they overlap, their amplitudes add arithmetically. In other words, they add with sign information. All right, so let's try to get some standing waves going.
Pretty good standing waves. 4.
Yeah. Okay, so there we have what, 1, 2, 3 full waves on the machine. So usually if you do this about right, you can get, well, it depends what the constraint is at each end, but in the simple case, you get an integer number of half waves on the wave machine. That's usually what happens if what's pretty close to the truth is that the two ends are both immobilized. I'm going to try a slightly different wavelength, or so here's a lower frequency, longer wavelength, so it doesn't look quite like as nice of a sine wave because it's pretty hard for your hand to go up and down in a perfectly sinusoidal motion. But that's pretty good. That's a pretty nice sine wave where we have approximately one complete wavelength on the wave machine. You want to try anything else, or?
And we could even try really fast.
Okay, then we can try to go a little faster. And it seems like now 1, 2, 3, 4. It looks like between 5 and 6 complete waves on the machine. Is there 1? I don't know, roughly 5 waves on the machine, I think. Cool. So this is the transverse wave machine. Transverse in that each little piece of medium is moving up and down, but the disturbance propagates from right to left. So I can send a little pulse from one end of the machine to the other. And you can see the speed of wave propagation. You can see how long it takes the disturbance to travel from one end to the other. And for a typical medium, that speed of wave propagation doesn't depend on whether the pulse is a narrow pulse or a wide pulse, or a high pulse that has high frequency content or low frequency content. There are some exceptions to that, but that's the case that we'll consider. And I have some numbers from earlier on about how long it took the pulse to go from one end to the other and how long the machine is, so I won't repeat that now. So here's a pulse. You can see the pulse go from one end to the other, and then there's a little bit of a reflection on the other end. So I put on this far end, I have a little can of water whose purpose is to absorb the energy from the end of the machine. So if that were perfect, then it would be like Professor Sabin's open window, and there's no reflection. The sound wave just goes straight out. So similarly, if this were perfect, then this transverse wave would its energy would be completely absorbed at the end. But you can see it's not perfect. A little bit of reflection comes back, but by far the majority of the wave gets absorbed at the end. So that was a pulse. I can also try to produce waves of fixed frequency. So here's a very low frequency wave. And you can see that the wavelength is pretty long. It seems like about, I don't know, I would estimate about 1.5 waves fit on the machine. We could try to measure it more perfectly. It's hard to measure it really perfectly because I'm not shaking the wave machine at precisely the same, a constant frequency. But anyway, you can see that the wavelength is pretty long when I shake it at a low frequency. Now I can shake it at a higher frequency, and we should see a shorter wavelength. And again, you can see that the wavelength is shorter because a larger number of waves, or a larger number of fractions of a wave, appear on the machine. Now let me shake it at a higher frequency yet. And again, you'll see that you can see a larger number of waves. And then I'll try to go even to a bit higher frequency. And you clearly see a larger number of waves on the machine. Looks like maybe, it's hard for me to focus on shaking the end of the machine and counting at the same time, but it certainly is a larger number. And then even a higher frequency, and this is definitely a larger number. I don't think I can go any higher. Let me see if I can go a little bit higher. That's pretty decent. And you can hear the frequency at which I'm shaking the end. You don't really hear it where I'm shaking it, you hear it where the wave reaches the little can of water on the far end. Okay, and then I'm going to reduce the frequency gradually. Okay, let me try even a slightly lower frequency. Okay, so I think that makes it plausible, this statement that the wavelength equals the speed of wave propagation divided by the frequency. So the speed of wave propagation is just a property of the medium. It's a property of this wave machine. And that's a property that you can see directly when I send a pulse from one end to the other. The speed at which that disturbance propagates is the speed of wave propagation. So the wavelength equals that speed of wave propagation divided by the frequency. So here's low frequency. Here's slightly higher frequency. Here's even higher yet frequency. And then here's a very high frequency. Yeah, so I think that's pretty good. And again, this is a transverse wave machine. So sound waves are not like this. Sound waves are longitudinal waves. These are transverse waves in that each little piece of the wave machine is moving only up and down, but the disturbance is propagating from right to left or from left to right. So those are transverse waves because the motion of each little particle of the wave machine is perpendicular to the direction of propagation of the disturbance that constitutes the wave. Let me try to get standing waves. So let me see what the lowest standing wave mode I can get is. I should be able to do lower than this, but I may not have the dexterity. Okay, now let me try a higher frequency. It takes a while for the motion to damp down when I change the frequency. It also takes a while for me to find just the right frequency where I'll get standing waves. That's not too bad. That's pretty good. Okay, let me try a slightly lower frequency. Okay, a moment ago you saw transverse waves. So the disturbance was propagating horizontally, but each little piece of the wave machine was only moving vertically. So that's called a transverse wave. This is going to be called a longitudinal wave because the wave will propagate horizontally and from left to right, say, or right to left, and each little piece of medium is also moving in that same direction, left to right or right to left. And actually it's sort of easy to see in this case the coupling between the nearest neighbors. So each one of these sticks, this is basically like a long stick, has a little white tip that glows in the dark, and it's pinned in the middle to make a pivot. And now if I hold this fixed and I hold this fixed and I move this one, then it oscillates back and forth. So if this thing wants to stay equidistant between its two neighbors. So if I displace it so that it's not equidistant between its two neighbors, then a bigger and bigger force develops the more I displace it from that, and it oscillates back and forth. So we have things that individually, when their neighbors are immobilized, behave like oscillators. And then also, if I move this one, then its neighbor wants to move proportionally. So we have like interactions between neighboring pieces. So now we have a medium in which waves can propagate, and the waves are going to propagate longitudinally, like that. And we'll see in another week, roughly, that this is what sound waves look like. So acoustical waves, sound waves traveling through air or traveling through water. In general, acoustic waves are compression waves, so the air becomes more dense, less dense, more dense, less dense, more dense, less dense, as the wave propagates that way. So this is actually a nice visual model of you can keep in mind for sound waves propagating through the air. So we're going to dim the lights again so you can really focus on these little tips. And so if I just make a disturbance go from one end to the other, that's fine. And then I think, so Bill's going to come over and completely immobilize the far end. And then I should be able, okay, so if we do that, then what reflects has to reflect with kind of the opposite sign. So I think then like more dense becomes less dense. Let's see. Okay, and then we can try to set up some standing waves. So let's go low frequency. That's kind of neat because you can really see that they become more dense, less dense, more dense, less dense, more dense, less dense. So you can really see that longitudinal waves are like an oscillation of how close things are together, or like in air. You can imagine if you're talking about sound propagating through air, it's like a local oscillation of a little bit more dense, a little bit less dense, a little bit more dense, a little bit less dense. The air molecules near one another. So this seems like, so we have a fixed point where Bill is on the opposite end. We have another fixed point known as a node where that's a velocity node. So you can have pressure nodes, you can have velocity nodes. We have a velocity node in the middle. We have a velocity node at the far end where Bill is. And we have almost a velocity node where I am because I'm just moving this thing pretty gently. So now I think if I shake it about twice as fast, we should increase the number of nodes. It's hard to see, I'm probably not shaking it just right, but that's pretty good. We've kind of created, so a node, you can see a node where the velocity or the displacement is always 0. So we can see I probably have 4 or 5 nodes. Let me go a little less quickly. So it seems like it's easy, that point is easy. Oh, let me see if I can go really slowly. If I go really slowly, I think I can make an anti-node where I am and a node where Bill is. That's not too convincing, I guess. What if, oh. Let's see, so if I go a little faster than I was going before, maybe we can get 2 nodes. That's pretty decent. So you can see, in addition to the ends, we have 2 nodes, kind of at the 1/3 and 2/3 points. And then I guess if we leave the far end completely free, then I think I
You'll be able to still get a standing wave.
I think I can get a standing wave that, yeah, let's try that. Let's see. So, and this is kind of like, I think what we might see, whoops. Okay, that's a little too much motion. That's a pretty good standing wave. So now I've got basically a node kind of in the middle, I think, and well, pretty close. And I think I have an antinode at each end. So that's kind of like an organ pipe that's open at the 2 ends. except it's a little bit different from what I described because it seems we kind of almost see another node close to the end. Are you good with this thing? Want to try it?
What are we trying to get?
Oh, I don't know. Let's see. So we could try standing waves of a variety of wavelengths.
So we got antinodes at both ends.
Yeah, so it seems like we have a node in the middle, antinode. This is kind of like an organ pipe open at the two ends.
Yeah, that's two
Uh,
waves, right?
Yeah, it seems like there's kind of a node here and there's kind of a node here. Yeah, but we have antinodes at the two ends at least.
And then three nodes, right? One in the middle.
Yeah, I think there's a node here, a node here, and a node here.
Yeah.
Yeah.
Okay, and then let's try.
Okay, so then we definitely have a node here, a velocity node.
And you got an antinode in the middle.
Now, by the way, also notice that the place where you have a velocity node, also known as a displacement node, you have a compression antinode. So the place where the position never changes, or the velocity is always zero, is a place where the compression is varying most rapidly. And then if we go over here, where the position or velocity is varying most rapidly, see the distance between those two particles doesn't change. So that's a compression antinode. No, that's a compression node, but a velocity antinode. So this is actually going to be interesting. It's kind of a useful thing to keep in mind. So the compression nodes and the velocity nodes, or displacement nodes, are out of phase with each other. And that's important to keep in mind when you think about how to prevent a sound wave from, what happens when a sound wave reflects off of a wall and you want to think about, do I want a reflection or do I want some kind of viscous damping? Sometimes it turns out that you want to put your absorber not right on the wall, but like a quarter wavelength away from the wall so that there's a lot of motion to dissipate energy. Like a thick pair of curtains, thick set of curtains, a little distance away from the wall so that, because the wall is going to be a velocity antinode, so then, no, the wall is going to be a velocity node, so then you have a velocity antinode a little distance away from the wall. It seems like now we have like a velocity or displacement node here, which corresponds to a compression antinode. And then we have a velocity or compression, a velocity or displacement antinode here. And you can see, again, the neighboring particles where we have the maximum change in maximum displacement. The neighboring particles are kind of staying a fixed distance apart at that point. So that's a compression node, but a velocity or displacement antinode. So I think it takes a little bit longer to get used to looking at compression waves, longitudinal waves, than it takes to get used to looking at transverse waves. So transverse waves, I think, are conceptually easier to follow, but longitudinal waves are important in that sound, which is a big motivation for studying waves for architecture, are longitudinal waves. So you kind of want to have a picture in your mind of these spaces between molecules of air varying and the velocities or displacements of the molecules of air varying.
Okay.
Yeah. So this is the longitudinal wave machine. So in this case, the wave moves that way from left to right, but actually it might be right to left, left to right. The wave moved from left to right, but each individual piece of medium also moves from left to right. So that's called longitudinal, meaning that the direction of wave propagation is parallel to the direction of motion of each little piece of the wave machine. And longitudinal waves are important, especially in the context of our course, because sound waves traveling through the air are longitudinal waves. So even though transverse waves are much easier to, it's much easier to get an intuition for transverse waves, and transverse waves are in fact the kind of waves on a guitar string, the waves on a piano string. So in many ways they're more familiar, at least to see, but you want to have in your mind's eye the picture of longitudinal waves for thinking about the way sound propagates through air. So let's just get this longitudinal wave machine moving, and I'm going to try to move it at a low frequency first. I have immobilized the far end, so I just put a big mass on the far end so that that far end won't move. And then I'm trying to find frequencies where I get a standing wave. So I get an integer number of half wavelengths staying on the wave machine, or in any case I get a pattern that stays fixed in space. And this is a pretty good pattern. So it seems like there is, well, so there's one velocity node. In other words, the velocity is always zero. There's a velocity node at the far end of the machine because that's clamped, it's immobilized. And that's kind of like what happens if you had a very massive wall at the edge of a room. You'll get a velocity node there. And then there's another velocity node about halfway across the machine. I want to see if I can point to it without messing up my frequency, but right around here you see a velocity node. So then it seems as if you see the velocity is always pretty close to zero there in the middle of the machine. But then you see halfway in between, so a quarter of the way, let's say 3/4 of the way across the machine, so halfway between where I pointed to in the far end of the machine, you see a velocity antinode, meaning that the amplitude of the back and forth motion is very big. It's maximal. Now one thing that's kind of interesting to observe is that the place where we have that velocity antinode, I misspoke. The place where we have that velocity node right here, we have a compression antinode. So the place where the individual piece of material is basically staying put is where the compression and rarefaction and compression and rarefaction and compression and rarefaction. In other words, the density, I mean, it gets, they get closer, farther, closer, farther, closer, farther. That's where that is maximum. So the place where the motion of the individual medium particle back and forth is zero is actually also the place where, in this case, the relative separation between neighbors changes the most rapidly. And so it turns out that the velocity nodes and the compression nodes on the wave machine here are 90 degrees or 1/4 of a wavelength apart. And then similarly with with sound propagating through air, the two things that you usually keep track of are the velocity or the displacement. I mean, the velocity is just the rate of change of the displacement. So it's how much the particles are displaced or how fast they're moving. That's one quantity. The other quantity is the change in pressure. So it's sort of what's the relative pressure with respect to the ambient atmospheric pressure? Okay, so now when I stopped to think, I lost track of what my frequency was here. Another thing I want to show you, which you've seen before in several contexts, but so I want to show you how the wavelength varies with the frequency. So it seems like I just found it. This looks like a different mode from what we were talking about a moment ago. It looks like Now the middle of the machine looks like a velocity antinode, and then it looks like kind of about 1/3 and 2/3 of the way across the machine. Kind of, it looks like are probably velocity nodes. Let me see if I can slow down again. So lower frequency. Okay, so now I think we're back to that kind of original motion where there's a velocity node in the middle of the wave machine. And then if I shake my end at a higher frequency, notice the wavelength will be smaller. So I can fit more waves on the length of the machine. And I can try to go faster yet. And I fit even more waves on the length of the machine. It's not always easy for me to find the magical frequencies where the pattern stays fixed, the standing wave patterns. And sometimes if I work at it for a while, I can. Okay, and then another thing I want to show you once the wave damps out, I think I can show you a rough illustration of how quickly the wave passes from one end to the other. I'll just do a pulse. Okay, so at least going from near to far, you see a pretty good pulse. Once it reflects, it's kind of a complicated pattern, but that's pretty good. So you can kind of see how fast the wave moves from one end to the other. Okay, so that's the speed of wave propagation on this machine. Let me try it, see if I can get a really good, yeah, that's pretty good. And remember that the speed of wave propagation equals the product of frequency times wavelength. So, and then if you just solve, that tells you the wavelength equals the frequency, C is lambda f, lambda is C over, right. The wavelength is the speed of wave propagation divided by the frequency. So the speed of wave propagation is fixed for this machine, but I can change the frequency at which I make the elements of the machine go back and forth. So at a low frequency, the wavelength is long. I could even go to an even lower frequency, and I think the wavelengths will be even longer. And then I can go to a higher frequency, and you should see a shorter wavelength. And I'll go to an even higher frequency. Oops, that's okay. So I kind of messed that up because I was going too fast. Let me try this again. So remember, the wavelength equals the speed of wave propagation divided by the frequency. So at very low frequency, we should see a very long wavelength. And it's easiest to see if I go at kind of a magical frequency where we get a standing wave. And then if I go a little bit higher in frequency, we should start to see a larger number of waves appear, or maybe we'll see one complete wave. Let's see. So I don't see a nice standing wave pattern yet. So then as I go at higher and higher frequencies, so this is pretty good. So now you see, not only is there a node on the far end, a velocity node, there's also a node halfway across. So it seems like we see two complete waves on the machine. And then I'll try to go a little faster, higher frequency. Now I think we see three complete waves on the machine. And it's kind of hard to get a coherent picture going much higher in frequency than that. I guess I could try. It just kind of looks like a blur now, but I think we're probably seeing something like 4 or 5 waves on the machine, but again, it's kind of, that's not as clear a picture. And then I can go back to a pretty low frequency. Yeah, so one thing I like about a slinky is that it's pretty easy to show both transverse waves and longitudinal waves on a slinky. So here we can do longitudinal waves where okay, so I displace the slinky that way, left to right, and the disturbance propagates left to right. And then I can also do transverse waves on the slinky, so I'm going to displace the slinky toward you, away from you, toward you, away from you, and you're going to see the disturbance still propagate in that same direction along the axis of the table. Yeah, so a slinky is a pretty good way to demonstrate both transverse and longitudinal waves. So I can make transverse waves with a slinky so I'm shaking the end of the slinky. Each piece of slinky is moving in this direction, but you can see the disturbance is propagating along the axis of the slinky. So okay, so those are transverse waves. Those are kind of like the waves on a guitar string. And then we can do longitudinal waves. So each piece of slinky is moving like this, and the disturbance is also moving like that. Yeah, that's pretty good. So these are longitudinal waves, which is more like sound propagating through the air. So all the action is happening along the axis of the slinky. Each piece of slinky is moving along the axis of the slinky, and the disturbance is moving along the axis of the slinky. Whereas this is a transverse wave, so each piece of slinky is moving perpendicular to the axis of the slinky, but the disturbance is propagating along the axis of the slinky.